Hi class, this is Dr. Nerz and I'm making you a video at home this week. We had a little snafu in that the videographer wasn't able to film the class last week. So this week it's going to be a little different in that you're going to access it using either YouTube or Google. Okay, so this is going to be a lecture, and ultimately the lecture is going to be on infrared spectroscopy, which I'll start in a few minutes, but first I just want to review what you're doing for this week. So you should be finishing the balance of Lab 3, and I did send you some information on this using Moodle. I gave you some guidance on all the questions. Realize that this lab, this week, which is Lab 5, is related to Lab 3 in that you're going to get an unknown sample that has some combination of an ionic, acid, base, and neutral compound. Okay? And again, and one thing I want to really focus on, and I wrote you this in the Moodle email, you're only going to have 3 of those 4. And when you're given that long list of compounds, it's only compounds from each class. For example, you can only have 1 acid, or 1 base, or 1 neutral compound, or 1 salt. Your goal is not to come up with a procedure to separate all of them. Now, what you're supposed to do in advance of class is find a couple people in your lab, and you can work with anyone from the lab and come up with a rough procedure for how you're going to do it. And realize it's really related to Lab 3 in that it does involve many of the concepts that are discussed in Lab 3, such as acid and base extraction. For example, a base can be extracted with an acid. Or last week when we were isolating caffeine, we were extracting phenolic compounds, tannins, catechins, flavanols, and so forth using base. In other words, those compounds were taken out of the solution, converted into their salt, and became very water soluble. I want you to think about that. Supposing you had a neutral compound like benzene, a basic compound like aniline, an acidic compound like benzoic acid, all mixed together. How could you separate them using acid and base chemistry? And that, again, is described in your lab manual. Unfortunately, in the doc, at least when I'm looking at the doc on the lab manual, the figures aren't coming up, and that's something I have to fix. But if you look at the PDFs, the pictures are in there, so look at the pictures. So using Lab 3, you should be able to come up with a rough procedure, but don't despair if you don't totally get it, because in the first half hour, excuse me, in the first half hour of lab, you'll have an opportunity, I really apologize, you'll have an opportunity to brainstorm with your group and with the TAs and myself to come up with a good plan. All the chemicals will be there. We just got to figure out how to separate them. And everybody's procedure is going to be more or less the same kind of procedure, maybe differing a little bit in quantities. But I wouldn't put an inordinate amount of time in it, but I'd put a few minutes into it starting to think about it, reviewing. There are great videos to watch. I really recommend that you watch all the videos that are embedded in the lab book, including the acid base, the one that's on the extraction of acids and bases. That's going to be very, very helpful. And in Lab 4, go to Lab 4 and start watching the videos on IR, because it shows you how to make up samples, how to run the IR spectrometer. We really want you to watch those before you come into class. It really helps. It helps you to understand it better, and it gets you started better. Okay? So the TAs are kind of anticipate that you've watched those videos before you come to class. Again, look in Lab 4. There are several videos on how to run an infrared spectrum and how to make up samples. Now, as I stated, because the lab itself is going to be more exploratory about acids and bases, I'm going to actually talk about infrared spectroscopy during this hour. Okay? Now, what is spectroscopy in general? Well, believe it or not, you've already carried out some spectroscopy, because when you were in general chemistry, perhaps in general biology, you probably used something called a Spec 20. And a Spec 20 is really a sort of UV visible spectrometer. And what you did is you probably made up a series of colored solutions. You probably remember doing this with Dr. Lucas. Maybe they were red or blue or some color, and they were varying concentrations. And then what you did was you took the sample and put it into the Spec 20, and you were told to pass a certain wavelength of light through the sample. Perhaps it was 605 nanometers, something like that. And you did this and you measured how much light or how much electromagnetic radiation was absorbed. And I believe you were probably studying the Beer-Lambert law. And maybe that comes back to you. Remember that. There was a relationship between how much light was absorbed and the concentration of the solution. And you can actually figure out the concentration of a solution that way. Okay? Now, colored compounds, again, are absorbing UV or colored compounds are absorbing visible light, but the UV, the visible range, is continuous with the UV range. Now, what all spectroscopy involves is this same concept, the idea of passing electromagnetic radiation through a sample and seeing which wavelengths are absorbed and the intensity of the absorption. In other words, how much is absorbed. Okay, this is of interest. This tells us something about structure. Okay, what I want you to realize is that whenever you pass light into a sample or you expose a sample to light, something happens to the sample. There's some kind of perturbation. I call it a perturbation. Something happens. Electrons jump, sometimes bonds break. Something happens to the molecule. Realize that whatever this perturbation is, relates to the energy of the electromagnetic radiation passing through the sample, or passing into the sample, some of which is absorbed, some of which goes right through the sample. Okay? Now, when you were working with UV visible light, what kinds of transitions were occurring? Well, UV visible light is kind of moderate in its energy, and what actually happens is you are promoting electrons from a pi to a pi star orbital, and you probably remember studying this in general chemistry, or perhaps from an N to an N star level, okay? And you like pump an electron up, and then the electron relaxes back down. But when that happens, energy is absorbed, okay? So, and that normally occurs, like a pi to pi star transition in a given molecule occurs at a discrete wavelength. Now, what was different about what you did in general chemistry is you weren't really measuring a spectrum. Supposing you had taken that same sample, put it in the Spec 20, and you just changed the wavelength sequentially. And you can do this with UV visible spectrometers. And you actually studied how the sample absorbed UV visible over a range of wavelengths. And you saw different absorptions and different intensities of absorptions that told you kind of about the whole molecule's behavior in UV visible light, like all the bonding, all the pi bonding, all the non-bonded electrons. What are they doing at different wavelengths? That would be a spectrum. And I want you to get used to the idea is that's what we're going to do in organic chemistry. We're going to measure spectra. In other words, we're going to study a wider range of wavelengths, the exposure of our molecules to a wider range of wavelengths. And from all that information, piece together the structure of the molecule. Okay? What kind of information do we need? As organic chemists, we need information about the atoms in the molecule, how many atoms there are, what types of atoms are in the molecule, and we also need information about the types of bonds in the molecule. Now, specifically, infrared spectroscopy is going to give us information about the bonds in the molecule. But before we get started on how this works, I want you to take a look at the infrared spectrum, okay? And this is the infrared spectrum. And you could look this up anywhere. You could look this up on Wikipedia, anywhere, okay? And these slides, by the way, are in your lab book in Lab 4. And it's probably a good idea to bring them to class. And this is showing you the range of wavelengths. So if we talk about electromagnetic radiation, there's a wide range of wavelengths, okay? The highest energy electromagnetic radiation are gamma rays. Actually, gamma rays and X-rays are kind of close to each other, okay? And the lowest energy that we consider are radio waves, all right? So as we proceed toward gamma rays, what's happening is the energy of the radiation is increasing and the corresponding frequency, because remember, these are wave phenomenon. They can be viewed as particles or waves, just like electrons can be viewed as particles or waves. So you probably learned in physics about the duality of light, that it has a particle and wave nature, and we're going to mainly look at them as waves right now, okay, as wave phenomenon. And as wave phenomenon, they have a frequency. So as we proceed toward the gamma rays, the frequency is going up and the energy is going up. And you can think about, what do they use gamma rays for in X-rays? They use X-rays in medicine. They use gamma rays to kill cancer cells, okay? This is very, very, very high energy electromagnetic radiation, and the perturbation that results from this is extreme. Now, when you were doing your Spec 20, you were working in the near UV and the visible. Colored compounds are the visible. And as I said, one of the possible transitions there is just electrons being promoted from a pi to a pi star orbital. But realize, if this is high enough energy, you could break bonds doing that. That's a pretty big perturbation. By the way, anytime we see color, that's what we're observing, or that's one of the things we're observing, are those kind of transitions. Now, what do organic chemists typically work with? We typically work with infrared, okay? Now realize, I don't mean to be skimming over this, of course X-rays are very, very, very important in determining the structure of compounds, because you've heard of the method known as X-ray crystallography. So I don't mean to say this is not useful in determining structure. It's extremely useful in determining structure. But as organic chemists, we tend to work with infrared and radio waves. So infrared, as you might expect, being lower energy, we're dealing with lower energy perturbations in the molecule. And infrared frequencies are really involved with the bond vibrations in the molecule. Radio waves are what we're going to deal with in a couple weeks when we talk about nuclear magnetic resonance spectroscopy, or NMR spectroscopy. And these are going to be the lowest energy of all. And of course, this is what's involved with getting an MRI. If you've ever had an MRI done, you're actually being exposed to radio waves, which are very low energy. Now, the important relationships that you need to know in terms of this spectroscopy is you need to know that E, the energy, equals H, which is Planck's constant, times frequency, okay? So this is saying energy and frequency are directly proportional, okay? The other expression is energy, right, equals Planck's constant times C over lambda, okay? So this is frequency here. Okay, lambda is the wavelength. Okay? So you're used to this. You're used to this expression. So when you were doing Spec 20 work or UV visible work, you would talk about setting the wavelength at, say, 550 nanometers or 600 nanometers. That's in the visible range. And in that case, right, what this is saying is that wavelength is inversely proportional to energy. So when you were at higher wavelength, you were actually at lower energy, okay? When we do infrared, which I'm going to explain in a minute, we're going to really be working with frequency units or something that's akin to or is related to frequency units. And when we do NMR, we're going to be working in frequency units. So you're going to find in infrared and NMR, when the numbers are bigger, okay, we're going to be at a higher energy. But generally speaking, when you're in the infrared or radio wave frequencies, you're at low energy. Okay? Now, what does the infrared spectrum involve? Okay? Well, when you run an infrared spectrum, essentially what you're doing is you're exposing the molecule to a frequency range that is 4,000 reciprocal centimeters or inverse centimeters to about 400 reciprocal centimeters. Now, our current IRs, I would say, go down to about 600 reciprocal centimeters. So again, get in the mindset of a spectrum. We're talking about a spectrum here, okay? So the sample is exposed to this whole range, and we study what wavelengths it absorbs, which wavelengths pass through, right? And what is the intensity of the absorptions when we actually get absorption of energy. Okay, now what do these numbers mean? These are called wave numbers. Okay, and wave numbers are 1 over the wavelength. Okay, so that means that this number is proportional to frequency. Okay, if we multiply it by the speed of light, it would be a frequency unit, but they're proportional to frequency, and these numbers give us convenient numbers. So when you're looking at the spectrum, when we're on this end of the spectrum, we're talking about higher energy, higher frequency, and when we're on this end of the spectrum, we're talking about lower energy, lower frequency. So I hope that makes some sense. Now, what's going on in infrared? Like, what's going on? What's happening to the molecule? Okay, so the basic deal is bonds vibrate. This is really, and you have to kind of take this at a relatively low level at this point, simply because we're really early in the course. But this is in your textbook, but it occurs later in the textbook. But I like students really early in the game to be able to figure out the structures of their compounds and to understand how we probe molecules and see molecules. This is how we see molecules. So for the first time this week, we're going to have some information about the structure of the molecule and not just circumstantial evidence, which is what we've had so far. So bonds vibrate. And what I mean by vibrate is that they stretch, kind of the way I'm moving my arm, and they bend. And I'm going to talk more about that in a minute. But they stretch and they bend. And when they stretch and bend at characteristic frequencies. So this must be really exciting to you, because in class, just these last weeks, you've been learning that bonds rotate. They're just rotating all the time, and then they sit in preferred conformations. Well, they also vibrate all the time. And when they vibrate at characteristic frequencies. So bonds vibrate, and then we can say different bonds vibrate at different frequencies. Okay? Different bonds vibrate at different frequencies. Okay? So, and what do I mean by a different bond? For example, a carbonyl vibrates, C double bond O, vibrates at around 1,700 reciprocal centimeters. Okay? Now, I'm using IR units there for a reason. Remember, that number is proportional to frequency, and all I'd have to do to convert it into frequency is multiply it by the speed of light. All I'd have to do to convert it into energy units is multiply it by the speed of light and Planck's constant. Okay? So that is really a frequency unit. So that bond vibrates at 1,700 reciprocal centimeters times the speed of light. That's its frequency. So it's always going at a certain frequency. Okay? A CH bond vibrates at around let's say, being a little more specific, around 2,900 reciprocal centimeters. Okay, so that's saying that CH bonds vibrate at a higher frequency than CO bonds. Now, what's going on with the IR? Why does a bond that's vibrating at 1,700 reciprocal centimeters absorb infrared? All right. The reason it absorbs infrared, the reason why bonds absorb infrared frequencies, is because the vibrational frequencies of bonds are in the same range in terms of frequency as the infrared part of the spectrum. So I want you to think of a bond vibration as being like a wave, because it is a wave. It has a wave-like nature. It has a frequency. And when you add to it infrared frequency that is the exact same frequency, what happens? What happens when you add waves together? Because something that has a vibrational frequency really is a wave. It has a wave characteristic. When you add frequencies together that are exactly the same, what happens? What did you learn in class when you were learning about orbitals, right? These should add constructively, okay? And when they add constructively, what happens to the wave? The wave's amplitude increases. So what I'm saying is that molecules have lots of different bonds. The bonds vibrate at characteristic frequencies. When the infrared frequency exactly matches the bond vibrational frequency. So in other words, if I put in exactly the frequency of this bond vibration, let's say it's 1700 reciprocal centimeters. When I input 1700 to a bond that's vibrating at 1700, that bond, you can think of it first as a wave phenomenon. The waves add and the amplitude increases. So what's the perturbation to the molecule? The perturbation to the molecule is that this bond, right, that was vibrating, I'm going to do my vibrations better in a little while, but this bond that was vibrating at a certain frequency maintains that frequency. But how's it going to change? Right? The amplitude's going to go up. So how does amplitude increase? Like this, right? But it's still going at the same frequency. That's all that happens to the molecule. When you put in, say, 2900 reciprocal centimeters, it's the CH bonds that are going to absorb. All right? Now that's one way to think about it. I'm going to give you another way to think about it in a little while. Another way to think about that absorption. Okay? So, okay, let's keep going. All right, that's just giving you like a basic idea about it. All right? Okay. Why do different bonds vibrate at different frequencies? Okay? Very often what's used is the spring relationship, which I can show you here. Okay? Let me just put this up here for a second. The spring relationship, which is given right here on the slide, okay? We can think of a bond as being like two balls on a spring. Okay? And that frequency is proportional to the square root of K over M. Okay? K is a constant, the spring constant, and M is the mass of the atoms, the mass of the balls on the end of the spring. So this is basically saying that the frequency of a spring vibration is inversely proportional to the masses. So in other words, if you put smaller masses on the end of the spring, right, smaller masses, it'll actually vibrate at a higher frequency. The spring constant is related to sort of like the tightness of the spring. And I always tell people to think about a slinky, which is a very loosely wound spring. Okay, think about a loosely wound spring versus, like, say you take your pen apart, you have a click pen and you take it apart, there's that little tight spring in there, right? Which one, if you compress it or stretch it, is going to vibrate at a higher frequency? Well, of course, that very tightly wound spring, or a spring that's made out of very heavy material, you know, inflexible material, that's going to vibrate at a really high frequency, whereas the slinky, right, is going to vibrate at a very, very low frequency. Think about holding onto the top of a slinky and dropping it. And that's the spring constant. Now, what does this correspond to? This corresponds to bond strength. So we're saying that if the masses are smaller in the atom, okay, the bond will vibrate at a higher frequency and therefore will absorb energy that is higher frequency. That's why CH bonds and OH bonds always vibrate at a really high frequency. Okay, they're around 3,000. On the other hand, if a bond gets stronger, for example, the CO double bond, it's a double bond. You've learned in class that double bonds are stronger. What would you expect to be even stronger than that? A triple bond, right? Triple bonds vibrate at about 2,200 reciprocal centimeters. Now, that's lower than a CH single bond, but realize the triple bonds have bigger atoms in them, okay? So one of the things we can use to kind of roughly predict the energy that's going to be absorbed is thinking about the masses involved and the strength of the bond. Okay, now, okay, so this is kind of useful because one of the things this is showing is different types of bond vibration. Okay, and I'm going to go back to this to go over what a spectrum looks like and look at some data, okay, before we leave this slide. But let me just talk about stretching and bending a little bit. When bonds vibrate, I was oversimplifying when I just showed one bond. When bonds vibrate, they really vibrate in sync with other atoms, okay? And this is kind of a hard concept, but for example, supposing I had a CH2 group like this, okay? These bonds will vibrate together like kind of in concert, okay? And the thing is, they have different kinds of vibrations. So, you know, and I always tell students this is a great time to do some exercise, some good upper body exercise, okay? These bonds, which are CH bonds, which absorb around 2,900 reciprocal centimeters. So when I put in 2,900 reciprocal centimeters, those bonds will absorb the energy, and they'll give a peak. A peak in the IR is indication that you're absorbing energy, okay? So these are the bond absorptions, and you should do this at home on your own. Like, this is good exercise. I always tell students this is the only exercise I ever get. I'm just kidding. But I do a little bit of exercise. This is a big part of it. So you can imitate stretching vibrations. What are they like? So this is the carbon, these are the hydrogens. So it's like this. Stretching vibration. Right? So what did we just learn? We learned that if the bonds are stronger, the vibration's going to be faster. Right? I mean, yeah, it's going to be faster, like if they're double and triple bonds. If the atoms are small, really fast vibration. And you're going to notice whenever a hydrogen's involved, the absorption's at a really high frequency. And what we said was, like they're vibrating fast, those CH bonds. But when you put in exactly the same frequency energy, what happens? Does the frequency change? No. The waves add, the amplitude increases. That's the transfer of energy. And then what happens? Much faster vibration, but bigger amplitude. That's all that happens to the molecule. That's a relatively mild perturbation. So stretching, this is what's called symmetrical stretching. Okay, this is my CH2 group. It's been going a little slow right now. I better speed up. But it's constant, right? Then there's anti-symmetric stretching, which is like this. Okay, that has a different frequency. That occurs in a different position in the spectrum. Okay, what else? Bending vibrations. These are slower. These are lower frequency. This is what's called an in-plane bend, right? And then there's an out-of-plane bend like that. It's a really good exercise. My shoulders are getting really, really stiff from that. Now, the thing is about IR, what does this indicate? This indicates that the same group, or the same atoms that are in concert with each other, will absorb multiple times in the spectrum. And this is an example of what you guys would call, let me see if I say this right, TMI, too much information. Like you would say, that's great. That's a wealth of information. That's unbelievable, right? There's 4 different ways a CH2 group vibrates, and they all have different frequencies, right? You think, that sounds fantastic. It's not so fantastic. It's too much information. So you're going to see we pretty much just focus on stretching vibrations, particularly during this first semester. Okay? All right, so I'm telling you that so you start to understand a little bit as to why the spectrum is really complicated. All right? So what we're going to do now is kind of focus in on a spectrum. So let's focus in on a spectrum for a second. Okay. Now, this is a spectrum that I drew. It's not a masterpiece or anything, but it does look the way most spectra look, okay? The spectrum is going to go from about 4,000 down to 400, okay? Notice the peaks are going down. They're not going up. That's just a convention. When we go in this direction, we're going to higher energy. When we go in this direction, we're going to lower energy. Okay, stretching vibrations, as I indicated, are higher frequency vibrations. So they tend to occur in this part of the spectrum, and this part of the spectrum is kind of a combination of low frequency stretching vibrations and bending vibrations, which, as I said, we're not going to pay as much attention to. Now, this part of the spectrum, the higher part, I would say above about 1,400 or 1,500 wave numbers or inverse centimeters, is the part we call the functional group region of the spectrum. And this is where many functional groups will absorb. It's also where CH and OH bonds will absorb. But you can frequently look at this part and learn something about which functional groups are in your molecule. But realize what this is telling you about are the bonds. It's telling you about the bonding in the molecule. This part down here is called the fingerprint region. As I said, this is the too much information part of the spectrum. There's a lot of overlap of peaks, And it takes quite a bit of expertise to interpret this, although you can learn how to interpret it. Certainly when I was young, I'm so old that when I was young, we actually did quite a bit of interpretation down here. Now, frequently what students use this for, in this time when you actually have NMR spectroscopy readily available to you, is that they will use this part mainly as a fingerprint of the molecule. So think about what this term means, a fingerprint. That's implying that it's very unlikely that two molecules would have the same fingerprint region. And what we mean by this is the landscape. In other words, the position of the peaks, but also the intensity of the peaks. Very unique for each molecule. Or like you could study a family of alcohols, all different alcohols. This part of the spectrum would look very similar, but you would no doubt see some distinction in the fingerprint part of the region because some bending or stretching vibration would be a little bit different. Okay, so you can actually fingerprint compounds. If you had some unknown compound, you could measure its IR, and clearly you could do some kind of a search, and you could match it up against known compounds and see if any known compounds matched your compound. If you had a new compound, obviously this would not work, although you might get some ideas about the structure. Now what this data is showing here is just what I just said about how mass affects the stretching vibration, or the vibrational frequency that it absorbs at. So if your molecule has CHs in it, okay, it will no doubt absorb around 3,000. Now notice what happens if you substitute a deuterium, and deuterium is just heavy hydrogen, twice the mass. What happens is the frequency goes down to 2100. CC single bonds are around 1200. So unfortunately, they fall in the fingerprint part of the region of the spectrum, and we tend not to pay that much attention to them, though we could. We can if we want. This is showing triple bonds versus double bonds versus single bonds. So again, this is the mass effect. Smaller atom, higher frequency of vibration, and higher frequency of vibration, to get that match with the electromagnetic radiation, means it's going to absorb exactly the same frequency. The amplitude of the bond will increase, and that's the only change that occurs in the molecule. And realize it is not a permanent change. Okay? What happens when you go from triple to double to single bond? Okay, what happens is you go from 2200 to 1660 to 1200. These are just approximate values, but it's showing how when the bond strength increases, all other things being equal, okay, the frequency of absorption increases. Okay, carbonyl C double bond O is 1700. C single bond O, unfortunately, falls in the fingerprint part of the spectrum. I hope you can see all that. Again, we're kind of at a disadvantage here. I'm actually using my TV to do this. Okay, this is the same information. Okay, what we have here is a much more involved table. There are all kinds of infrared tables. You will see there are infrared tables in your textbook. There's an infrared table in your lab manual. There's one that I always give out when I have quizzes. And by the way, your first quiz will probably be something about spectroscopy. There's all kinds of tables. There's all kinds of stuff we could look at. We could spend our lives looking at absorptions and memorizing them. But I don't want you to do that. Okay, I really don't want you to do that. The approach I take with infrared spectroscopy is what I call a landscape approach. So what I'm going to do is call up some spectra that I like to use for this. And we're going to just start looking at spectra. But before I do, I'm going to put them up, and you can see what a real spectrum looks like just for a second here. So I have these. We have a wonderful spectral database. But before I end, I'll try to show you that as well, where that is. Okay, so I have some IR spectra that I just picked out to demonstrate certain points. Okay, now these are knowns. I have the structure here, but I'm going to hide the structure for a minute. You're like, I already saw it. I don't think I can hide it. No, I don't think I can get it off the screen. But this is the spectrum of 1-propanol. And I'm just going to kind of show you, if you look at this, you'd say, oh yeah, that kind of looks like what we saw before. There's like some absorptions occurring in the fingerprint region, and then there's this rather complex region we would call the functional group region. But before we do that, let's just talk about a couple things. Okay, first of all, I want to talk again about this stretching vibration. this is another way to look at this, okay? I want to talk a little bit about polarity. The only thing you see in IR, okay, are groups that have some net dipole moment, or bonds that have some net dipole moment. Bonds that don't have a dipole moment don't show up. And this causes some complexity in IR, because it would be so cool if we could figure out how many of a certain bond we have. Like, wouldn't it be cool if we could just look at a peak and somehow quantitate the area of the peak the way you do with, say, a GC, and, you know, integrate it, get the integral. If we could do that, we could figure out how many CH bonds we have, how many OH bonds we have. But there's a problem in IR, and the problem is that CH bonds and OH bonds, part of their absorptivity, or the intensity of the absorption, is related to the number of the bond you have. So in other words, if I have a lot of CH bonds, I'm going to get a big absorption. And frankly, we should expect a big absorption for CH bonds because organic molecules have a lot of CH bonds normally, right? But here's the problem. The intensity of the peak is also related to the polarity of the bond. And bonds that are more polar absorb more. They absorb more energy. So the intensity of the peak is also related to how polar the bond is. And I'm going to demonstrate this with this propanol spectrum in a minute. But I just want you to think about the absorption a different way. And this is like a more physical way to think about it, like in terms of like the actual atoms involved. So we had this kind of wave idea. I was saying when the waves match, they have the same frequency, the amplitude goes up, and that's registered in the molecule as an increase in amplitude in the bond vibration. Okay? And you see it in the spectrum as an absorption of energy. In other words, that energy went in and it didn't come out on the other side. Okay? Or not as much came out on the other side. So, what's a more physical way to think about it? Well, you could think about, say, for example, a carbonyl group, which I've brought up already. Now, you guys have been learning about, now this could be like an acetone or, you know, some other structure, like say this is cyclohexanone. This bond has a dipole moment. And you've been studying in class about dipoles. This carbon is delta plus, this oxygen is relatively delta minus. So what you want to think a little bit about is how this is going to interact with electromagnetic radiation. And a good way to think about electromagnetic radiation, right, is as an infinite number of perpendicular, oscillating electrical fields and magnetic fields. Okay, so like there's an electrical field that's oscillating plus minus, like that, at some frequency. And then perpendicular to that, there's a magnetic field that's oscillating, but there's an infinite number of them. Now, if I just consider the oscillating electrical field, okay, what I'm talking about is I'm talking about a field that's oscillating in terms of charge at some frequency. We could just think of light as being that, you know, just like it's like you have a field where one end is negative and one is positive, but it's constantly switching back and forth at some frequency. What is that frequency? Well, it could be infrared frequency. So right now we're talking about infrared frequency, all right? But that's what light is. That's a way to think about light, and it's just the frequency at which it does this that determines its energy, okay? But I want you to think about physically why polarity is so important. What happens if we put a molecule, if we put a carbonyl group, let's say, in that oscillating field? Well, you know that this bond is a field of charge, right? It's a field of charge density. And you would say, well, the way you drew that carbonyl, whatever it's attached to, this end is delta minus and this end is delta plus, okay? Now think about how your dipole moment is going